Okay, so we're going to do a quick walkthrough of problem number 6 that was on our Unit 9 assessment. This seemed to be one that caused a decent amount of trouble for many of you. The first thing in any of these problems is what you always want to do is identify what you were given. So in the first part of the problem here, it says that the fuel tank that we're considering that would have hydrogen gas in it has a total volume of 150 liters of hydrogen. So in our given section, we are going to say we have 150 liters of hydrogen. But remember, when we deal with any gases, as we go back to discussing things with gas laws, the temperature and the pressure at which that gas is found is also important. So we have a pressure of 20 atmospheres, and the units will become important here in just a minute. And then we have a temperature of 25 degrees Celsius. Now, what we need to find, what the problem is actually asking us for, it wants to know how much mass of water vapor. So what is the mass of water vapor that could be produced? So this is going to go back to some of our original stoichiometry concepts. If we start with a balanced equation, can we actually figure out how much stuff we're going to need? So we want mass of water vapor. So because of the fact that we're looking at some sort of stoichiometry question here, the easiest thing for you to do would be to set up a BCA table. The first thing we need with the BCA table is to figure out what our balanced equation is. So we've got hydrogen gas here that we're starting with. We know it's saying that it's being burned in the presence of air, and so it's going to combine to form water vapor. So what is the other reactant? Well, the only thing in the air that's going to combine with to form water vapor would be oxygen. So we've got hydrogen gas plus oxygen gas, and that will yield water vapor. And it's important again to note that we need a balanced chemical equation. And if you look at these numbers really quick, you see hopefully quickly that you need a 2 here and a 2 here. So that gives us a ratio of coefficients of 2 to 1 to 2. So now that we have a balanced equation, we can go ahead and set up the initial information for our BCA table. We don't know exactly how much oxygen we're going to need, but we know that since there's plenty of it in the atmosphere, we can assume that we have excess. We don't know, or we should say we don't have any water vapor produced in the beginning. And then the question said that we have 150 liters, but don't forget that the only thing that's allowed to go into our BCA table is moles, and 150 liters is not in moles. Now, we learned from the lab that we did last week that there is a conversion that we can use for that. We can use our 22.4, our molar volume that we were able to calculate with the lab we did a little while ago, but the problem is, if you remember, that molar volume is 22.4 liters at STP. And so 1 mole of any gas equals 22.4 liters, but it's only at STP, standard temperature and pressure. And we look at the conditions here at 20 atmospheres and 25 degrees Celsius, that's not a standard temperature and pressure. So we could do a whole nother problem here where we use the PVTN tables, and we could figure out exactly what the volume would be at standard temperature and pressure. But we've also learned something new recently that will make our lives a lot easier here. So we've got our PV nRT formula, our ideal gas law. And in order to use the ideal gas law, we need a pressure, a volume, we need the number of moles or temperature, we need 3 of those 4 things. And in this case, we do. We have our pressure, we have our volume, we don't know the number of moles. R is our ideal gas constant, which is listed for us here, and we have the temperature. So because we have enough of the variables, we can go ahead and use that information to complete the formula for PV equals nRT. You might want to rearrange this initially, so you want to divide both sides by RT in order to get number of moles by itself. So this would cancel, and we'd end up with number of moles equals PV divided by RT. With any equation, if you go back to what we did and learned about how to use these formulas at the beginning of the year, you want to do a little bit of inventory. So number of moles would equal the pressure would equal, the volume would equal, ideal gas law constant would equal, and temperature would equal. So what are those values? Let's go back to the problem and see. Number of moles, we know that's what we're looking for. So we know that that is going to be our big question mark. The pressure is listed for us as 20 atmospheres. The volume is listed for us as 150 liters. Our ideal gas constant, you have 2 choices. They're on the back of our periodic table. This is where the atmospheres becomes important, because in the units here for our ideal gas constant, we see atmospheres present, which means that we need to use this 0.0821 versus the 8.31. If it was 8.31, if you look at the back of the periodic table, you'd see that this would not be atmospheres, it would be kilopascals. And since the problem was given to us pressure in atmospheres, we're going to go ahead and continue to use the 0.0821. So for this problem, it's 0.0821. And then for our temperature, it's 25. But in any gas law problem, don't forget that we have to add 273 to convert it to Kelvin. And so we're going to end up with a value of 298 Kelvin. If we plug all these numbers in here, we end up with N equals our pressure, which is 20, times our volume, which is 150, divided by our ideal gas constant, 0.0821, and multiply that by our temperature, which is 298. If you go ahead and solve for this right now, you should get an N value, or a number of moles value, somewhere in the neighborhood of 122.6. So now what? Now what do we do with that problem? Well, all we were trying to do is we were trying to fill in this information here because we had to put moles in our BCA table. So now that we have the number of moles of hydrogen gas that we started with, we can go ahead and list that here, 122.6. Change, our change row, how does this get affected? So we have excess of this. We know that we're going to lose 122.6 here. For oxygen, it's a 2-to-1 ratio. So we're going to use half as much oxygen as we have hydrogen. So we're going to have a loss of 111. I'm sorry, I can't do simple math. And so we're going to have 66.3. And for the amount of water produced, it would be equal to the amount of hydrogen that we lost. And so that would be 122.6. So after, we have none of this left over. We have plenty of oxygen left over, and we were able to produce 122.6. And don't forget, this is moles of water. So how do we go from moles to grams? Because we go back to what the problem was originally asking us for. It said that we wanted the amount of grams of water vapor that would be produced. So then we take our 122.6, and again, this is moles of water. And for every 1 mole, we have 18 grams of water. That value is the molar mass. So straight from the periodic table, 2 hydrogens, 1 oxygen, that gives you molar mass. That tells you how many grams are in every mole of water. If we do the math for this, we get 122.6 times 18, and that equals 2,206.8. And again, because moles of water cancels here, we're left with grams of water as our only unit, and so grams of water. So that should be your final answer. I hope that was helpful. If you still need some additional help, just come see me.